Thank you for inviting me to this workshop and welcome everyone to my virtual presentation on label-efficient visual abstractions for self-driving. This is joint work with Asim, Kashyap, Aditya, and Eshed. There's two dominating paradigms to self-driving. On the one hand, we have the modular pipeline, where the image to action mapping problem is decomposed into a set of modules that can be independently developed by larger research and development teams. And this is therefore one of the main approaches that is followed in industry. It also leads to an interpretable representation because one can expect the interfaces between the individual modules. However, the design of the pipeline and the models often requires expert decisions, which are not necessarily optimal. And these modules are often trained in a piecewise fashion, where one module is not trained for the ultimate goal, which is safe and efficient driving, but rather for some intermediate loss functions, such as an object detection loss. Another idea is to represent this complex sensor to action mapping directly through a neural network that is trained using either imitation learning or reinforcement learning. Such an approach is very simple to implement, and it allows for training the parameters of the network end-to-end for the actual driving task. However, existing models do not generalize as well as modular pipelines, as they are missing the inductive biases that are incorporated into these pipelines. They are also less interpretable and they require a lot of data for training. Let me show you a video of some of the results of an imitation learner that we have obtained on the Kala simulation environment. As you can see, even in simulation, scenarios can be quite complex, with pedestrians walking on the road or traffic lights that need to be obeyed. And there's many things that can actually go wrong, such as not respecting a traffic light, stopping in front of a reflection by misdetecting it as a pedestrian, crashing into another vehicle, or driving off-road, or simply hurting other people. Luckily, only virtually here. Now, there is a model that lies between these two approaches and that tries to combine the benefits of both, which is called direct perception, where there's a neural network that maps the sensory input to some intermediate representation. And then there's either hand-engineered or learned vehicle controller that maps this intermediate representation to the action. Now, this intermediate representation should be designed in a way such that it captures all information that's necessary for driving, but not much more. And this on its own is a difficult task, of course. Now, here we are in the workshop on multimodal learning, and there is some modalities to consider here. So there's, on one hand, the modalities of the sensory input, which could be either images, LiDAR, radar, or GPS. We will not consider this part in this talk here. We will simply consider an image-based input for this talk. But there's another modality I want to argue that is relevant here, which is the modality of the intermediate representation. And that's the focus of this talk. What intermediate representation should we choose? Should we choose semantic segmentation? Should we choose 2D or 3D bounding boxes? Should we choose depth, or should we choose motion or optical flow? There's a couple of related work that have looked at this problem before us, and I want to quickly walk you through. First, I want to present a imitation learning baseline that we use in our approach. This is actually one of the state-of-the-art imitation learner on Kala that was published at ICCV last year. It's called CILRS, and it's a conditional imitation learner that maps observations to actions but also conditions on an additional command, a high-level command that's provided by the route planner that tells the system to go either left or straight or right at the next intersection. For imitation, training data is obtained almost fully automatically by simply recording data with a web camera and at the same time also recording the signals of the pedals and the steering wheel. So that's relatively cheap. However, standard imitation learning algorithms typically suffer from the problem of causal confusion, such as the inertia problem, where the model observes the vehicle speed being 0, leading to, in most cases, an acceleration of 0. This is undesirable because in these cases, the vehicle after stopping will never start again. In order to combat this problem, in this SILRS approach, the authors presented a two-stage model where an image is input into this backbone here that predicts now both the current speed as well as a feature representation, which is concatenated with the measured speed and fed into a second conditional module. The advantage of this setup is that now this backbone, this perception module, is encouraged to produce feature representations that are actually causally relevant for driving by also trying to predict the speed. And the paper shows that this actually helps in solving this problem. Still, this conditional imitation learning approach does not generalize very well to new environments. And the reason is simply that it overfits to the training environment. At the same time, it has very large training variance, which means if you change the seed that is used for training the model, which changes the initialization of the random weights in the network or the order with the data with which the data is sampled, then the variance on the test set of the actual driving metric will be very large. This, of course, is undesirable because it makes models very difficult to compare. Another approach is an approach that we've presented at CORL 2018, which is called conditional affordance learning. This is closer to this direct perception approach that I've presented before, where observations are mapped to some low-dimensional intermediate representations we call affordances. And then there's another controller that maps these affordances to actions. These affordances in this case are very low dimensional. We just have 6 dimensions in this case. For instance, the angle with respect to the road, the distance to the lane, the boundaries, or to other cars, etc. So we just include the affordances which we think are relevant for driving. Here you can see an example. We see the distance to the next car. We have this red box, which is the hazard flag. If there's a pedestrian appearing in the red box, then there's a hazard affordance to be detected. Here we detect speed signs in this green box. So it's all quite hand engineered. These affordances are then automatically extracted from the simulator at training time to train a perception module that predicts these affordances. And at test time, then a controller can take in the predicted affordances for the actual control problem. The advantage of such an intermediate representation is that it decouples perception and action and therefore has been shown to generalize better. However, in this original paper here, we considered a rule-based controller, so it wasn't differentiable and trainable. And one important problem of this approach is misspecification of affordances, which happens quite easily, which means that if the set of affordances is not specified such that it fits all scenarios, like for instance, these areas are not determined in a way that they, for instance, also hold for intersection scenarios, then the model, of course, will not work in these scenarios. Now, a number of papers have considered more general, more classic computer vision representations as intermediate representations for the self-driving task. Here's one example. in the paper Does Computer Vision Matter for Action, they analyzed various intermediate representations, including semantic segmentation, depth, normals, optical flow, and albedo, for the ability to help in this generalization problem. And they found that intermediate representation improved results, and they got consistent gains across different simulations and tasks. They also found that depth and semantic provide the largest gains, where semantics helps most in the urban setup, which we are considering here in this talk, and depth helps most in the off-road traversal setup. And they also found better generalization performance using these intermediate representations. They also produced a nice little video that shows the key idea quite nicely, which I'd like to show you now.
Our planet is teeming with intelligent life. Biological creatures sense the world and move through it to survive and reproduce. And soon they may be joined by artificial creatures, robots designed to see, move, and act. How should such robots be constructed? Researchers have explored two approaches. One uses structured intermediate representations to link perception and action. These intermediate representations are produced by computer vision algorithms that perform object detection, semantic segmentation, or three-dimensional layout estimation. The intermediate representations produced by such algorithms are then used as a basis for action. This approach to building intelligent systems has thrived in the fertile plains and the soaring towers of academia. Yet it is threatened by a powerful newcomer. A vigorous species is invading from the distant lands of Neurips. This species couples perception and control directly with no intermediate representations. Pixels go in, actions come out. The new species poses a threat to older inhabitants of the fertile plains. If actions can be produced directly, what is the role of computer vision? Are intermediate representations needed at all? We study this question by training agents in simulated environments. Some agents use computer vision to build intermediate representations. Others do not. In urban driving, our agents need to move through busy city streets to reach their goal. On off-road trails, the agents ride on rough mountain roads where a wrong turn can mean an untimely end by plunging off a cliff. In battle, the agents face alien monsters in a fight for life or death. We find that agents that use computer vision are hardier. They drive better, survive longer on mountain trails, and emerge victorious in battle. Even when their vision is imperfect, agents that use intermediate representations are stronger. Here we can see agents that use computer vision to drive through city streets.
There's other ways to incorporate information such as semantic segmentation into the end-to-end learning approach. One way is to use latent space distillation, where in this case here, a teacher network with privileged information, so with access to ground truth semantic segmentation and ground truth affordances, is trained for the control task. And then a student network that has access only to the RGB image is also trained for the control task, but at the same time tries to minimize its latent embedding, the distance of its latent embedding with respect to the segmentation embedding of the teacher network. And there's more evidence, more related findings that demonstrate that intermediate computer vision representations are actually useful for generalization. There's works that demonstrate the utility in reinforcement learning environments. There's works that demonstrate the utility in generalizing from synthetic data to real-world driving. And there's works that demonstrate the utility in indoor navigation tasks. However, so far there has been no systematic study on label efficiency and the representation granularity that is required for training the intermediate representation. Of course, in practice, this is of high relevance because we cannot assume that this labeled data is available just as it is available in a simulator or in some data sets that have already been annotated. But in practice, we will probably have to create a new data set and acquire labels for this data set. So the critical question here to ask is, what intermediate representation should we choose such that we have minimal effort, minimal manual annotation effort? And this is precisely the question we ask in our research on label-efficient visual abstractions. Now, what is a good visual abstraction? Well, first of all, it should be invariant. It should hide irrelevant variations from the control policy. Let's look at this example here on the right side, where we have these two bedroom scenes that look quite similar in terms of their content, but the appearance is dramatically different. So if you look at the pixel space, so one is a training example, one is a test example, these distributions are very far from each other. Now the goal of such an intermediate representation is to map this pixel space into some representation space such that these points in that representation space move closer together. In this case, we have used a semantic segmentation of these two images, which looks closer to each other compared to the original images that are further in pixel space. A second desired property is universality, that the model is applicable to a wide range of scenarios, that the intermediate representation is not restricted, as in the case of conditional affordance learning, to very specific towns or cities or environments, but that it can actually deal with environments it has not seen before. We also want the representation to be data efficient in terms of memory and computation. And importantly, we want it to be label efficient. We want it to require little manual annotation effort to obtain. In this work, we consider semantics as the intermediate representation, as this has shown to be one of the strongest intermediate representations in prior works, and as it encodes task-relevant knowledge, for instance, the road is drivable, as well as priors or explicit biases about the world, for instance, in the terms of grouping of similar pixels. Furthermore, 2D representations can be processed with standard 2D convolutional networks for the policy, so they are quite easy to deploy in this end-to-end imitation learning framework. A disadvantage, however, of semantic segmentation is that it's very time-intensive for obtaining the actual labels. If we consider one Cityscapes image, the authors of Cityscapes remarked that it took about 90 minutes for the annotator to annotate one Cityscapes image in terms of its semantic labels, just because it's very difficult to annotate these images at a very high level of detail. But is this detail really required? Also, are all the classes really relevant? This is what we ask in this research here. So the research questions that we ask is, what is the trade-off between annotation time and driving performance? Can selecting specific semantic classes even ease policy learning because the policy network is not distracted by irrelevant information? Are visual abstractions trained with few images competitive to visual abstractions trained with large number of images? And how many images are actually needed? Furthermore, is fine-grained annotation important, or can we use also more coarse-grained annotations which are cheaper to acquire? And finally, are visual abstractions able to reduce the training variance that we've seen before? Here's the model that we consider. We have a segmentation and detection part here on the left, where the input is an image X, which is transformed through a visual abstraction network into a visual abstraction representation, which we call S. And then we have a standard conditional imitation learner on this visual abstraction that takes this visual abstraction S as input. And in addition, the navigation control command N and the velocity at the current point in time, because we consider only the current image and not previous images, so the model doesn't know anything about the current speed if we don't add it to the system, and produces the control output, or the action C. Now composing both these mappings together yields the final policy, which takes an input, image X as input, produces a visual abstraction, and then produces finally the action. We use two data sets for training this model. We have NS images annotated with semantic labels, so we have pairs of X and S's. And we have NC images annotated with expert driving controls, so these are pairs of X and C's. And what's important to note here is that we assume that the number of annotated images with semantic labels is much smaller than the number of images annotated with expert driving controls. As the number of images annotated with expert driving controls, a larger number of images annotated with expert driving controls is easy to obtain by simply recording driving sequences and also recording the steering wheel and the gas pedal. We train this model in the following way. We first train the visual abstraction network using the semantic dataset S. We then apply this network to obtain the control dataset. So we apply this visual abstraction network to all the input images of the control dataset and obtain this dataset C that way, and then train the control policy using this control dataset. The model we use is the CILRS model from Codevilla et al. From ICCV 2019, which is illustrated again here on the right-hand side. The input to this model in our case is not an image, but a visual abstraction, which is embedded into a latent code from which the velocity is predicted and which is then also concatenated with the current velocity for a second network that takes the navigational command as input and finally predicts the control. The output is the control and the velocity at the current point in time. And the loss we use for training this model is the same as in the original CILRS paper, just minimizing the L1 loss of the action and the L1 loss of the velocity. We consider multiple different visual abstractions in our analysis. From the color simulator, we derived 14 relevant classes, which comprise all classes in order to label all the pixels in the image. What you can see here is the privileged segmentation, which is what we give as input to the model if we assume that the model has access to the ground truth. This serves as an upper bound for our analysis. In this case, you can see the ground truth semantic segmentation map for all 14 class labels. We also experiment with a reduced number of labels. So we removed some of the labels that we deem not relevant for the driving task, so that we only obtain 6 relevant classes, in particular 2 stuff classes, road and lane marking, as well as 4 object classes, like car and pedestrian and red and green traffic light. Again, this is the privileged segmentation. This is the ground truth segmentation for an upper bound analysis. Next, we consider the inferred segmentation. We use the ground truth 14 class model, 14 class segmentation to train a semantic segmentation model, in our case a ResNet with a feature pyramid network with a segmentation head, in order to predict a semantic segmentation for the images in the Kala simulation for all the 14 classes. You can see a typical example of such a prediction here. Then we consider the same network for inferring only 6 classes. So the network can spend more capacity on these 6 classes that we deem more relevant for the driving task. But again, you can see that the output, of course, has some noise compared to the ground truth. And finally, we consider a hybrid visual representation for which training data is even easier to acquire. This hybrid representation considers only 2 stuff semantic classes, road and lane marking, and in addition considers the 4 object classes only in terms of their bounding boxes, which can be retrieved using 2D detectors. So we obtain 2D detections for vehicles, pedestrians, and red and green traffic lights. Annotating these bounding boxes is of course easier than annotating the precise boundary of the objects. So it decreases the annotation effort. And what we're interested in is, well, does it still lead to plausible policy outcomes? So let's look at our experiments. We evaluate our approach on the Kala 084 no crash benchmark. There are 2 towns. There's a training town and a test town. At testing, there is a random start and a random target destination selected at the test town, and the goal is to successfully navigate from the start to the target location. And the metric that we use is the Kala metric, which measures the percentage of successfully completed episodes. In other words, the success rate. So we run the agent many times from many different start locations to many different end locations and see how often it can complete the sequence. In this no crash benchmark, there's multiple levels of difficulties integrated. The easiest one is the empty scenario, where there's no dynamic agents. Then there's a regular scenario with about 65 agents in the entire town, and the dense setting, which is the most challenging one, with 220 agents that move dynamically in addition to the agent that is trained. The weather situation also changes between the training and the test conditions. You can see the 4 training conditions that are observed during training here at the top, and the remaining 10 test conditions here at the bottom. So these are observed in town 2, and the training weathers are observed in town 1. As you can see, some of these weather conditions are actually quite challenging, such as rain and sunset simultaneously. The first experiment we did is we wanted to identify what are the most relevant classes for the privileged agent. We started with all 14 classes, which include road, lane marking, vehicle, pedestrian, green light, red light, sidewalk, building, fence, pole, vegetation, wall, traffic sign, and other. And then reduced to 7 classes by removing building, fence, pole, vegetation, wall, traffic sign, and other from this set of classes. We further reduced to 6 classes by removing the sidewalk class, and furthermore reduced to 5 classes by removing the lane marking class. What we see here is in green the relative ratio of success for the different number of classes in the empty, regular, and dense scenarios, and the overall performance here on the right. What you can see is, of course, the empty scenario is easier than the regular and the dense scenario, so performance degrades. But the tendency is similar in all of these plots. So let's look at the overall plot here on the right. The tendency is that if we reduce from 14 to 6 classes, we don't see a drop in performance. We actually see sometimes even an increase in performance. However, when we reduce to 5 classes, then we see a drastic performance drop as the lane markings are removed. This means the sidewalk is not as important, but lane markings are for sure important for the model. This might not be surprising, but this experiment provides systematic evidence that this is actually the case. Here's an example in form of a short video. What you can see now on the next seconds on the left are the privileged agent with all classes, then the privileged agent using only 6 classes, and the privileged agent using only 5 classes. You can see here is that the success rate of the privileged agent with 14 or 6 classes is high. However, with 5 classes, the agent often timeouts or collides. We also did the same experiment using the non-privileged client, using the inferred segmentations. We can see a similar behavior. We see that the performance is slightly lower than with the privileged information. However, the performance is actually quite on par, and in some situations can even be a little bit higher than with the privileged information, which is already an indicator for the fact that the quality of the segmentation might not necessarily need to be as good as for other tasks for this driving task, because the control policy can compensate for some of the inaccuracies in the output of the semantic segmentation. But we see a similar behavior as in the previous experiment, where the 6-class representation consistently outperforms the 14-class representation. This is interesting because it means by labeling less classes, we can achieve higher performance on the tasks that we actually care about, the self-driving task. We therefore use the 6-class representation for all following experiments. Next, we investigated the impact of the number of annotated images for the learned visual abstractions. We tested 400 labeled images, 1,600 labeled images, and 6,400 labeled images. Here you can see again the plots for the empty, the regular, the dense, and the overall performance. Let's focus on the overall performance. We see that the performance slightly drops. The success rate slightly drops when going from 1,600 to 400 images. However, in all of these cases, the performance is actually quite similar. In particular, there is not much difference between 1,600 and 6,400 images, indicating that actually not that many images are required to be annotated for successfully completing this task. In contrast, prior work exploiting semantics on Kala uses millions of annotated images, which on Kala is of course easily possible, but in the real world, annotation time matters. We also analyzed the impact of our even cheaper hybrid representation. The performance of the hybrid representation roughly matches that of the standard semantic segmentation, as we can see in the overall performance plot here. However, the annotation time of the standard segmentation is roughly 300 seconds per image and per class, while in the hybrid case, because we just have these 2D bounding boxes, we require roughly only 20 seconds per image and class for annotating. So we have another 10-fold increase in annotation time using this hybrid representation that comes as with very little degradation in terms of driving performance. Here are some qualitative results. On the left, we can see the standard representation, and on the right, we can see the hybrid representation, both trained with 1,600 images. We can see that they are both successful in many scenarios. The next thing we investigated is the training variance problem. The training variance problem is evidenced here. If we use the standard SILRS imitation learner that operates on raw images as input, we can see that depending on the training seed, the variance or of the success rate in the test town is very high. So for instance, for seed 1, we have 26% here and 48% here. Or in this case, we have 0% success rate for the dense setting and 18% success rate for this seed 5. On contrary, we found that the training variance is significantly reduced when using segmentation-based intermediate representations of visual abstractions. Here we look at the hybrid representation, the most efficient visual abstraction that we consider in our experiments. We can look, for instance, at the coefficient of variation, which is basically denoting the standard deviation divided by the mean. You can see that this coefficient of variation is significantly lower, almost by a factor of 4 in all of these settings compared to the image-based imitation learning baseline. This indicates that these intermediate representations can actually be quite beneficial in alleviating this problem of training variance. Finally, we also compare to several state-of-the-art models on the imitation learning task. What we see is that our hybrid model is actually comparable with these state-of-the-art models. Here we can see the latent distillation approach. Here we see CLRS and the conditional affordance learning approach, which is not reaching the performance level of SILRS or our technique. Here's a qualitative comparison to SILRS. Let me briefly summarize now. We have shown that exploiting visual abstractions leads to more robust driving models. And higher segmentation accuracy does not necessarily imply better driving. It's also interesting to note that only few of the commonly used semantic segmentation classes are actually relevant for solving the driving task. And lane marking is critical for good performance. We also saw that only few annotations, only 400 or 1600 annotated images are enough to solve the driving task almost as good as with much more annotated images on the Kala simulator. And we've also seen that hybrid representations have the potential to even further reduce annotation costs without losing driving performance. We've even seen that box-based representation can improve the performance on certain dynamic classes, and that the training variance, while high in behavior cloning, should always be reported, and that visual abstractions can significantly lower the training variance. This slide maybe summarizes our approach best. On the left, we can see the semantic segmentation obtained from 6,400 finely annotated images with all 14 classes, leading to a success rate of 50% at an annotation time of 7,500 hours. While on the right, we have our efficient hybrid representation that's trained with 1,600 coarsely annotated images on 6 classes in only 50 hours with a policy success rate of 58%. Now this concludes this part. In the last few minutes, I want to quickly give you an outlook on a next generation KITTI dataset that we had in preparation for a long time, but now finally this summer we'll release it. It's called KITTI 360 because it provides 360-degree imagery and it comes with novel, exciting forms of annotation. This is what some of the trajectories that we've recorded look like. And I think it's a particularly interesting data set also for the multimodal community because it comes with all kinds of information that can be considered jointly. For instance, it comes with the classic front-facing stereo camera, but also with a 360-degree fisheye camera that allows for a full 360-degree surround view. It has the classic Velodyne HDL64 laser scanner, but also a SIG push-broom laser scanner for better coverage of buildings and trees. And it comes with an IMU GPS localization system as the original Kitty dataset. There are about 83,000 frames of 4 cameras and the laser scans, covering a driving distance of roughly 73 kilometers. All frames are accurately geolocalized such that additional information, site information, for instance from OpenStreetMap, can be utilized. And we have annotated the dataset using semantic labels both in 3D and 2D, and the semantic label definitions are consistent with the Cityscapes dataset such that cross-dataset generalization performance can be analyzed. Furthermore, each instance is assigned with a consistent instance ID across all frames. So we don't only have individual IDs for individual frames, but we have it all consistent in 3D over the entire sequence. Here are some illustrations of what the dataset looks like. Here we have a point cloud, colored point cloud using the RGB cameras. We have the bounding boxes. The dataset is annotated using 3D bounding boxes, but in contrast to the original KIDA dataset, we have also now bounding boxes for the road and the sidewalk and the trees and the buildings, etc. These bounding boxes are used to infer per pixel labels for each point in the point cloud and also per point instance labels. And we have developed an algorithm that can then map this information into the 2D image domain to yield approximately accurate 2D ground truth, both for semantic segmentation and for instance segmentation. We also output a confidence so that we know in which regions of the image we are confident about the estimates of the ground truth and in which regions we are not. Finally, we've produced a little cinematic video trailer, which I'd like to show you here now at the end. We will release this data set this summer, and we'll hope that this data set fosters new, exciting research areas. With that, I want to thank you for your attention, and I want to also thank my sponsors and point you to our blog page if you're interested in our research. I invite you to have a look at this link here. Thank you very much.
Hi everyone, I'm Haidong Zhu from University of Southern California. Today I'm presenting our paper, CAPAR, Category-Based Proposal Analysis for Referring Relationships. First, let's introduce the task of referring relationships. Referring relationships is to localize the subject and object entity based on a given query. We plot an example here to show the difference between the detection problem and referring relationships. The two examples on the first row are the detection results for category person and bags. Detection results may have more than one output, since there might be multiple person or bags there. To distinguish different people or bags, we need to localize the specific objects given some corresponding descriptions, such as the person with a phone or the bag next to the person. We show these two results on the second row by showing the corresponding localization results for subject and objects in the query respectively. Finding the object in the image that satisfies such kind of relationship query is known as referring relationships. Specifically, in the referring relationships problem, we have a query triplet in the form of subject, predicate, object as input, and the output the localization result for the subject and object entity. We generate the bounding boxes for both subject and object and use these bounding boxes as our final output. There's little previous work directly related with the referring relationships. For the most related method, SSAS, it focuses on generating the heat map based on the attention for subject and object separately. This method applies the predicate as a shift and generates such shift between the object and subject iteratively before generating the final heat map for subject and object entity. Such results are feasible for generating corresponding relationships, but SSAS also has many problems. Since it takes all the subjects into consideration, most of the objects that do not belong to the category of the subject or object will still be taken extra time for evaluation. Also, the heavy computation of heat map makes the resolution for SSAS to be low, which in fact reduces the accuracy of the final referring relationships result. We propose a proposal-based method which is called CAPAR to solve such problem. The CAPAR system consists of two different modules, one for generating the candidates for those proposals that is in the same category as input, subject, and object, which is called the category-based proposal generation module, and another module, which is called the predicate analysis module, is to evaluate the predicate information between the candidate object and subject to figure out which pair should be the most suitable for the given predicate triplet. We first focus on the category-based proposal generation. The category-based proposal generation module generates the proposals based on the category names of the entities enclosed in the bounding box. It first generates the proposal candidates for subject and object respectively. For all bounding boxes generated, it ranked the proposals based on the language embeddings for the category name of the subject and object respectively, and then selects the top K proposals as the detection result. In our experiment, K is set to be 5 for both subject and object. After category-based proposals generation, we can greatly reduce the computational complexity by reducing the number of candidate proposals. We will describe our method more detailedly in the following few slides. For the category-based proposal generation, the first step is to generate the proposals candidates. We apply the RPN initialized with an VGG16 that is pre-trained on the ImageNet and fine-tune it on our dataset. We set NMS in RPN as 0.6 and generate 300 proposals for each image after RPN to feed it into the category-based proposal generating network. All the proposals are extracted the feature vector with a ResNet 50 network pre-trained on the ImageNet for future processing. In the meantime, we extract the language embedding for the noun phrases of subject and objects. The noun phrases are the single words for the category name, which is processed by glove embedding system with 300 dimension vector as output. After the language and the visual features vectors are extracted, we concatenated the language embeddings with every visual embeddings from the proposals to rank all the visual proposals according to their category names. The score will be evaluated with the MLP and ranked all the bounding boxes for the subject and objects separately. After every bounding boxes are scored, we select the top K proposals according to the scores from highest to the lowest. At this step, we have an output for subject and object score respectively for every entity in the image. So after these, we already have a result for every proposal in the image according to their names about whether they are the subject or the object described in the query. Since we only extracted 5 objects for evaluation, the overall combination is only 25. This greatly reduces the complexity of computation for the second stage. In the second stage, we evaluated every subject-object pairs with the predicate analysis module. Since different from the first stage, where every subject and object are taken into consideration separately, in this stage, we combine the subject and object together to evaluate the score for the predicate relationships between them. So the first step of the predicate analysis is to evaluate the pairwise subject-object that is generated by the previous module. For predicate analysis, instead of using the feature vector, we use the 7x7 feature extracted from the ROI pooling layer from the RPN network, instead of any type of combination of feature vectors. Compared with using the feature vectors, ROI pooling feature both preserve the localization information as well as the appearance information. Moreover, it still keeps the combination between the location and the appearance of different parts in the enclosed bounding box. This greatly helps for the final accuracy for predicate analysis. We made a Appalachian study for evaluating the benefits of using such feature instead of feature vectors in the results part, which we will introduce later. With the two concatenated features, we applied the predicate classifications for every subject-object pairs we extracted from the category-based proposal generation module. We apply a predicate predictor for every predicate so that we can extract another score for the classification about the score for every pair. This score can be seen as the predicate score. So after this step, we have 3 scores: subject score, object score, and the predicate score. For the final prediction, we evaluate the score for the production of these 3 numbers and get the subject and object bounding boxes with the highest numbers as our final prediction. We evaluated our results on 2 public datasets, VRD dataset and VG dataset. Both of these 2 datasets have the form of subject predicate object queries, and we both use top 70 frequent predicates. Detailed descriptions about these 2 datasets are available in the paper. We show our results here in the following slides. We first show that the results for the subject and object IOU for both of these 2 datasets. From the table, we can see that we have comparable results on the subgroup category on the VG dataset, and we outperformed all other splits comparing with all our 4 other baselines. Besides IOU, we also evaluate the recall on both 2 datasets. The recall is defined as having the IOU of the predicted boxes and the ground truth boxes greater than 0.5. We show the results for VRD dataset first. Note that since SSAS only generates the heat map, we can only evaluate the top 1 boxes that generated by this method. Our method outperforms all other methods on both subject and object. We also evaluated the score for our 2 different modules variations, Kapar CP and Kapar PA. Kapar CP is the result for the category proposal generation, which can be known as a score for subject and object. And Kapar PA is the result for the predicate analysis, which is a score for the predicate. We found out that even without any predicate analysis, simple result from kappa CP still outperforms the SSAS. This shows that even without any predicate analysis, the proposal generation result is much better compared with heat map. Also, results for simple predicate analysis is higher compared with heat map analysis. This means that with fewer candidate proposals, we can reduce more confusion for predicates analysis. Moreover, we found that combining the score for category-based proposal generation and the predicate analysis, we can have the best result among all variations. Having both category information and predicate analysis, we can have a better result for referring relationships. We also made a comparison on the VG dataset. Note that since VRD do not provide results for VG dataset in their code, we only made a comparison between SSAS and two modules for kappa. We still shows that we have a better result comparing either module with SSAS, and the best result when we combine the two modules together for localizing the subject and object according to their query triplet. For a population study, we evaluate whether the detection bounding boxes is good enough for predicate analysis. We made a comparison between the top 1 and top 5 boxes for ground truth and our detection result. The evaluation metric is the predicate recall from the predicate analysis module. We found out that the recall for detection is pretty similar, as only using the ground truth bounding boxes for predicate analysis. We also showed that compared with only using the highest score boxes for predicate analysis, top 5 has a recall over 90% for both detection results and ground truth, which means that by only using the top 5 candidates, our method can greatly reduce the time complexity while not do great harm to the final accuracy. For the feature selection, we also made a comparison between different choices of feature embeddings for predicate analysis. We made 4 types of embeddings that can be concatenated pairwise: ROI pooling feature, phrase vector, visual vector, and 5D location vector. We made a comparison between using the ROI pooling feature and the different types of concatenation of feature vectors. We found out that using the ROI pooling feature has the better recall score compared with other combinations. Compared with single visual feature vector or 5D location feature, the results from the ROI pooling layer has both visual feature and location feature, which provides richer information for predicate analysis. We show some visualization results here. All these 4 examples shows the pretty good referring relationships results. Take the last image as an example. We would like to ground a person with a hat. There are several people in the image, and for referring relationships, we like to ground a specific one. Using the predicate analysis method, successfully localize the specific man that is with a hat, which is the man we really want in this image. So this is all for our presentation, and thank you very much for listening.
Okay.
Cool. Okay. I guess I'll start. We're a couple of minutes early, but that's fine, I assume. Yep,
I'm fine with that.
Yep, cool.
Just
Let's
talk a
go.
little bit longer.
Yeah. Okay, so hi. Thank you very much for inviting me. I had great plans to do lots of research in multimodal work, but that didn't quite happen. I'm actually going to talk a little bit historically, but what I'm going to talk about is about how you transition computer vision systems from research into the real world. And I'll use lots of historical examples from my career, but I think it's still relevant today. I think even though we have a large number of computer vision systems that are really working in the real world, I think not many people understand what you need to do to transition there. And even up to quite recently, we found we're learning a lot in this domain. So that's what the subject is here, making stuff work in the real world. As Bodo said, so I lead now the All Data AI group at Microsoft Cambridge. So what does All Data AI mean? Well, the acronym is ADA, and you may have heard of Ada Lovelace as the first computer programmer. And we can discuss Babbage Lovelace contributions to the early computation, but something that she did very definitely observe in 1840, so nearly 200 years ago, is that computers, or the concept of computation then, was really about calculate, what we would call today a calculator. And specifically, it was mainly about how to get bombs to fall efficiently on your enemies by calculating missile trajectories. That's what people really dreamt of. And what Ada Lovelace observed was that the difference engine might act on other things beside numbers. And she gave examples of music. And she probably had in mind vision and understanding documents. So what we do in our research group is very much look at the areas of AI that deal with complicated data structures, complex real-world data structures. I call it big data, small data, and funny-shaped data. In terms of technologies, we do things like graph neural networks. We look at Bayesian deep learning. So when you're lacking data, so the small data scenario, which I claim is actually very, very common, lots and lots of real world examples, you actually don't have lots of labeled data. So that's something we're very interested in. And something we do a lot on is machine learning on programming languages. So if you were to look at my recent publication list, you would find actually most of it is in programming language, or not most, I run a large research group, so I don't do a lot of publication every year, but where we are publishing is in the area of programming languages. And that's partly because I'm really interested in how we can design new programming languages for AI and machine learning. I still do some computer vision, but my main focus is programming languages. Before I came to this research group, I worked on something which you may have heard of called the HoloLens. So, if anyone's unmuted, can you see any sort of pointer? Does my mouse pointer transmit?
Yes.
Yes, it does. Great, thank you. Yeah, and the video is without sound. That's intentional. So the HoloLens is a device being worn by Julia Schwartz here. Julia Schwartz is an amazing designer and engineer. So she's the person who understands the computer vision. So she was designing these user interfaces. And what's happening here, and sorry, I spoke over the start of the video, we don't see it. The HoloLens device has a Kinect-like camera in it. It is tracking her hands, providing full 30 DOF 30 degrees of freedom tracking for each hand. And she's here showing the HoloLens user interface that she designed and built based on our hand tracker. And I'm going to lead up to how we got that hand tracker to work in this device, which is about 100 times less compute than an iPhone 7. Right, so this device, the device has compute twice of a large iPhone, but for us, for hand tracking, we have basically the amount of an Apple Watch, or 1/100th of an iPhone 7. So how do we make state-of-the-art hand tracking run on an iPhone 7? Before I do that, I'm going to do a very quick sort of historical run through computer vision problems that I've been involved in, and in particular how we turn them into products or how we turn them into something reliable enough for people to work on. So as Bodo said in 1996, he correctly said I finished my PhD in 97, but I went to get a job as a postdoc in Oxford in 96. Let me recommend to anybody listening, it's a very bad idea to get a job as a postdoc before you finish your PhD. It's very difficult to get two jobs done at once, so try to finish your PhD before you go anywhere. So I went to Oxford, working with Andreas and in Mike Brady's group, and our idea was, well, robots would need vision to navigate the environment. So, could we take a video sequence like this and somehow recover a structure and motion or simultaneous location and mapping? Could we recover the blue camera trajectory and maybe some representation of the 3D structure represented by the red dots here? Could we figure that out? For those of you, I'm sure most of you know, but I think it's fun to see the inspiration of classical computer vision then. This amount of data, even in 1996, was an enormous amount of data, megabytes per frame. So, and the tools we had there were pre-deep learning. So the tools we had essentially were mathematics. So how do I turn a complicated image like this into mathematics? Well, we use tools from the 70s. So in the 70s, psychologists were trying to simplify or understand human vision. And Jitendra will almost certainly show these same videos later. The two of us started using them about 2 years ago in our talks. I claim simultaneous invention. The psychologists were trying to find out what's the simplest signal that I can have to sort of understand motion in the scene. So here we can see the person with the rotating wheel. On the rotating wheel, there were some illuminated dots, and those dots alone serve to give you some representation of what's happening. But I'm not sure you definitely say, oh, that's a rotating wheel. What's interesting is when you attach the dots to an object that we know well. So you may think maybe this is a standing human, but when we play the video, it becomes, I would say, blindingly obvious that this is a walking human, even though we've reduced the entire motion to a tiny number of dots attached to the human. You might not know what this is before I hit play, but once we do hit play, then I think you form a very strong percept of what's happening. It's a human. You can do tests and show that people are actually pretty good at estimating the gender of the people in these videos, even though there's only a tiny number of dots, and they can do activity recognition from this data. So I think you probably have a hypothesis that this is a person who walked in, climbed a ladder and started painting. Maybe you have an idea what this person is doing. I don't know how you're dealing with lockdown at the moment, but I think a lot of us are doing this sort of exercise, or at least during dense lockdown, people were doing this sort of exercise rather than running and cycling. So from this tiny amount of information, there's lots more of these. You can find them on the internet. We can determine what's happening in a video sequence very easily. And of course, the trick used from structure and motion is, well, if I could turn each frame of my video into something like that, then I would have a mathematical problem, not a sort of nasty visual recognition problem. I would just do some stuff with these 2D trajectories. So we knew all that, and that's what we were trying to do back then. And we could not make it work, right? So 96, there was no way we could deal with this amount of data. There was no way we could get decent structure of motion from this data. So what did we do? We did strategy number one that Zisserman said to me at the time, why don't we do it for something simpler? Do it for turntables. And we can do special mathematics, right? That deals only with the rotating case. And I was like, Andrew, no, that's pointless. Like, we're not going to learn anything. It's never going to be useful. Why make the problem easier? It was a brilliant idea, as all Zisserman's ideas are, obviously. So the idea was we're going to just look at turntables. And if you just look at turntables and you apply the same trick, track the 2D points, now it turns out you get super accurate structure of motion. So we have 10 milliradians of accuracy in the angle estimation for these cameras. We got nice 3D points. Everything worked beautifully. We could go further. We could now use the beautiful cameras, and because we had a blue screen background, we could get nice 3D models. And even today at CVPR, we're looking at 3D is somehow an area of computer vision where we like doing 3D because you kind of know you've got it right. One of the things we were proud of then, and I'm still proud of now, is that we went to sort of great effort. We engineered the hell out of it, as I say, to build a system that was really robust, got nice 3D models. We went sub-pixel in our edge detection here, which meant that each input image is only, you can see the pixels here. I don't know, this is maybe 30 pixels high. And this 3D model derived from this sequence is maybe 1,000 polygons high in this direction. So we were able to get super fantastic super resolution, 3D super resolution from 36 low-res input images. So this is 99 I said 96, so 99 by the time we got this working. And we thought, this is brilliant, right? We've got a 3D modeling system, and because it's on this turntable, we can actually believe in it. Remember, 20 years ago, computer vision didn't work. So it was a very unusual situation. We actually thought we could make this work. So we made a startup, and this was almost a disaster. So why did we think we could make a startup? And this applies today. You will have algorithms or results where you think, great, I've done something novel. And what we did there was novel, which was, although the object was on a turntable, we had no other information about the video. So everything was recovered purely from the images in an uncalibrated manner. It was definitely cool. Even today, people love 3D models. And most importantly, we could see a way to make a reliable product using this technology. It turns out, despite being novel, cool, and workable, it was also entirely useless. And why was it useless? It was useless because the kind of industries we were trying to sell it to were very special industries. The only people who cared about 3D modeling were special in that they were the car industry or the movie industry. So, but let's first of all look at those advantages from a research point of view. We were really excited that we needed no calibration. But we'd already said you needed a turntable and a blue screen. So once you've got a turntable, you may as well drive it with a motor. And once you're driving it with a motor, it's harder to make it unequal angle than it is to make it equal. So really, the system that you could have built from this had zero of the research advances that we made were relevant at all for the system. You'd be far better off just engineering a system with a blue screen and a motor-driven turntable and calibration grids and all of that. So it was just a stupid idea. We tried, oops, sorry. Anyway, we didn't know it was a stupid idea. So we went around to lots of movie studios. We weren't that interested in auto industries because, I don't know, we weren't car people, we were movie people. So we went to lots of movie studios and everyone said, yeah, lovely work, really nice, useless, don't care, don't want to buy it. Somebody said, oh, this picture, what are these? And we explained those are the cameras. And it's like, how do you get the camera position from those videos? And we explained structure and motion. You have to simultaneously recover the 3D points and the camera position, otherwise it doesn't work. So it turned out that the movie people really, really wanted the cameras. Why did they want the cameras? They wanted the cameras because they wanted to take video like this one and stick 3D objects into it. If I flash forward for a bit beyond how it works, I'll show you what they wanted to do. What they wanted to do was they had the idea of maybe they would have children in a school like this one, and maybe they would have 3D virtual candles in the air above them. That was what they wanted to do. But of course, we didn't know that. We thought they just wanted 3D models. So if I go back to my 3D models. Oops. So what did we do? So we went back, and this time we had to take on the hard problem, right? We had carved out a nice, easy problem for ourselves. This time we had to do it for real. So we went back to the problem that we first tried to solve. This is the program we built, just showing it running. So feature point detection, feature point tracking, classic computer vision. Each of those feature trajectories corresponds to a 3D point. So using ransack algorithms and so on, then we can build this representation, which is a 3D point cloud and a moving camera, which is sort of simultaneously recovered. Of course, this point cloud is horrible. So when we thought we were going to be selling a 3D modeling tool, we were kind of throwing our hands in the air because this point cloud was so horrible. But it's just enough. If you look here, right, you can see a kind of an L-shaped 3D structure here. And that is just enough, if you remember the original sequence, to identify the wall of one of the buildings. And then what I'm going to do is select the 3D points on the wall. That's now this collection of 3D points. And now I can stick a 3D object onto the plane defined by those points. None of this stage is automatic. Right? It's fully automatic to get up to the 3D points. And now, of course, we wrote loads of code to automatically find the planes in the scene and automatically try to build 3D models. Pointless. The users are much happier indicating what they want to stick the object on by just drag selecting the scene. So here this user has put on a little ladybird. That's our kind of test case. And what we're trying to do is now, oops, this is intentional, but I was going to do it earlier, is play the video. And what we want to do is check that the ladybird appears to be stuck correctly to the scene. And I think you'd agree that it looks as if, aside from its blueness and its bad lighting, that the ladybird is well stuck to the screen. Now, even then, late 90s, people said, well, that's pointless because you just explained to me, Andrew, that these people don't mind, these people, the movie industry, don't mind manual labor. In fact, there's, even today, there are teams of sort of young interns in basements in Los Angeles and London, manually marking up frames of movie in order to achieve special effects. And you might say, well, couldn't you just stick the ladybird in position every 2 frames or every 10 frames? And then, it would be fine. You could interpolate between them. Well, it's interesting to see actually how much the ladybird has to move. So when I have the background switched on, you can notice the camera jumping around, but you don't realize that the thing is moving tens of pixels in every frame because your visual system will stabilize the ladybird to the background. So when I turn off the background here, you can see that in fact there's an awful lot of movement of the ladybird from frame to frame. So it wasn't possible to do it manually. It was lucky. We actually saved quite a bit of money for the movie industry and got awards and everything. Let me talk a little bit about how you do this. So, we're used in computer vision to, there is a benchmark data set, and it is valuable to the community to collect a benchmark data set. So then, our benchmark data set wasn't enormous. We gathered 100 test videos, just by walking around Oxford and generally getting videos. We built metrics on those videos, and just as we can do today, just as we overfit on data sets today, we easily overfitted to these metrics. Before we did that, first of all, because we're building something for real and because we weren't caring about the publication, all we did was read every single paper and implemented every known algorithm. So sometimes I see people responding today saying, a reviewer may say, why didn't you compare to algorithm X? And our tendency today is say, oh, well, algorithm X is commercial or the source code isn't available, so I don't need to compare to it. When you're selling, there's not a question of whether you need to compare to it or not. You have to compare to it, right? You have to be as good as the competitor. So there's extra work there. But the other thing you notice after a while, once you've implemented 5 algorithms from the literature, implementing number 6 is incredibly much easier. Once you've implemented 20, implementing number 21 is incredibly easy. So we really did just implement everything known at the time. Yes, we had secret sauce. Yes, we had stuff that we were really proud of in there, but it kind of doesn't matter, right? The point is we made it work. The other thing we do a lot was break our metrics. So we would have some metric like number of inliers or number of points with error less than 0.2. Any metric like that, the system, it will break it. It's like you will overfit. So what it did when we had lots of, our metric was number of points, within 0.2 pixels, the system would take the hit of losing all the points every 20 frames. So it would score a massive error every 20 frames, but the RMS over the sequence was kept low by that. And it only had to do short range optimizations. So we had to change our metrics because even without us trying, we weren't trying to cheat or anything. We were just trying to make the system as good as we could. Optimizing on metrics gave us bad brokenness, and we had to change the metrics. And then, of course, after a while, we got 100% on our test set on videos that we cared about, having fixed the broken metrics. So then we got 100 new videos, threw away our old test set. And of course, our success rate was down to 50% again. So even though we had gone really good on our training set and we thought it was representative, this is something I like to say when you're trying to sell something. This is not Kaggle, this is the real world. When you're building something to ship in the real world, you don't have access to the test set. The test set is going to come after you ship, right? When it gets in the hands of customers. So everything you're doing is on the training set. You better make sure that you are not overfitting to your training set. You better make sure that you're keeping 80% of it away for very occasional testing. So it's nice not to be in sort of that kind of competition, but of course you're in competition with your competitors. That's why they're called competitors. We got to use it on, this is one of the early films that we got to use it on. This does have sound, but it's terrible. Oh, it's Troy. It's they're
coming for me.
Lots of wooden ships.
The wind is bringing them closer.
Lots of wooden actors.
This will be the greatest war the world has ever seen. We need the greatest warrior.
Apparently, it's a really good film. I've never been able to sit through it. It's the acting is so terrible. So that's what you see on film. This is what was shot. There's a single boat moving on moving water. Those green dots are not there in the world. Those are our debug output that we're using just to check if we're getting anywhere. So we got one boat moving on the water, another boat behind it, and a convenient boat placed almost collinearly with these two boats, which didn't help us. So that was, a nice hard sequence, much harder than we dealt with before, which we were able to do for that film. Of course, it got used in this clip that I showed you earlier, which is what my child is most interested in. And it was most useful for television. So we never got an Oscar. I'm very sad about not getting an Oscar. But we got something called an Emmy, which I explained to my mother. I'm Irish. My mother's Irish. I explain an Emmy is a thing that isn't an Oscar. That's a good definition of an Emmy. So that technology comes forward then decades later to the HoloLens device that I showed you at the start. So the same core ideas, although I did not work on the head tracking for the HoloLens, it was George Klein, and one of the most beautiful pieces of engineering I've ever had the privilege of observing. So the HoloLens, as I said, is a single device, total compute power, about the size of a high-end mobile phone or a mid-range laptop. On that device, 4 grayscale tracking cameras, a Kinect style depth camera, and an RGB camera. Apologies if I'm pointing to the wrong one. I think no, there's the depth camera, there's the RGB camera. And that device takes a video view of the world through the 4 cameras, where again, in real time, battery powered, tiny amount of compute. It's applying the same sort of technologies. And this is shipped, a few years ago, we shipped Connect V1, we now ship Connect V2. And a beautiful piece of engineering here in making all of that run in, thousands of times less compute than we had available even in '96. So for me, having done, the sort of structure of motion work and got that working, I want to say another story about shipping something. I'll talk about shipping, body tracking, and Connect. And this is going to be a story of how I was working on exactly the wrong thing and my colleagues were working on the right thing. But we still had some innovations that we made that were valuable to shipping. So I moved to Microsoft 2004, 2005. And in Microsoft around then, there were people like Jamie Shotton, John Wynn, Carsten Rota, Antonio Cremonesi, who were working on this stuff that I'd never really thought about before, which was, could you take every pixel of an image and could you label every pixel in the image with the category label, the semantic segmentation label? I will try and turn off the sound here. Maybe I'll just sort of randomly scrub through the video. So again, 2004, they have a real-time system that can do semantic segmentation on camcorder video coming in through the boat. Amazing piece of technology based then on decision trees. Now you would use something more accurate, more efficient. We'll see. I was interested in working on something else. I wanted to work on a scene where the motion was more complicated than we had done from structure of motion. Structure motion is actually pretty simple, right? There's 6 degrees of freedom: camera, X, Y, Z, and camera orientation, 3 DOF, maybe focal length, so maybe 7 degrees of freedom. And the structure motion problem works essentially in this world of no motion, other than that caused by the camera. So it's a rigid world. So I was interested in, could we do something to track motion of the human body? And state of the art around then, this is ICCV 2007. State of the art around then is we could take an object, do the silhouette, and this paper was, which I'm very proud of, was about generating multiple hypotheses of from the silhouette, frame by frame, and then piecing together those results to give you a tracked 3D human body. So it was a good system. It kind of only worked on sequences quite like this one, and it was 1 minute per frame. So around then, Xbox people came to us, and they had this vision, and basically their vision looks like what you see here. They had this idea that they would stick a camera in front of the television, and then the camera would follow human motion, and people would jump up and down and play in front of the camera, and it would be amazing. It was a sort of an interesting moment, because as I was the person working on body tracking at Microsoft at the time, I said, it's lucky you pay me a lot of money to work on body tracking, because I can tell you that what you're proposing is impossible. Please don't try to do it. So that was my advice, and I thought I'd save the company a lot of money by not trying to do something as foolish as Kinect. And why did I say it wasn't going to work? Well, they wanted it to be much better than the computer vision state of the art in terms of motion ability. It needed to run on 10% of an Xbox 360, and an Xbox 360 is a machine is a PC that was designed in 2003. So it needed to run in 10% of a 2003 era machine, and it was really important that it could track 2 people at the same time, which we knew was doubling the number of degrees of freedom in the problem. So it was like, look, no problem. I'm serious computer vision researcher. I can tell you this is a foolish endeavor. They said, but we've got this new 3D camera. And I was like, yeah, okay, new 3D camera. It does make it a bit easier, but I'm still telling you this is like impossible. And then they said, it's funny you tell me it's impossible, because we've got this young programmer in Xbox. So this is someone who was not a computer vision PhD student. This is someone who just kind of thought about the problem and said, well, why don't I make some like 3D model of the person, with some polyhedra, and then maybe if I go into the T pose at the start of the game, and then I update my model every frame, 30 frames a second, maybe that'll work. So this was quite a good moment, because quite a good embarrassing moment for computer vision expert who's loudly claimed this is impossible, to be shown that a couple of Xbox engineers, now admittedly Xbox engineers are genius programmers, but it's shown that a couple of Xbox engineers could make this thing work. Now, of course, you probably know why something like this isn't going to work, right? The difficulty is, yes, if you get into the T pose, it'll track beautifully, but you know that after a while, it's not going to track. Something's going to go wrong. It's going to collapse. And the problem that they had was, yes, it worked great, but after, 10 seconds, some amount of time, the system would collapse, and there was no way to recover other than design games which have 10 minutes of gentle motion followed by getting back in a T pose, which wasn't a realistic prospect. So what happened? And this is, I think, the fun bit. I was the person working on body tracking. None of my work was helpful here, right? Because of the way we were trying to do it just wasn't thoughtful. Jamie Shotton, my colleague, was working on semantic segmentation using random forests. So Jamie essentially thought, how can I turn this 3D computer vision problem into a semantic segmentation problem? So he had the idea of taking the input image and then inferring, dividing the human body into 32 different segments, inferring the body parts. And the trick was that the semantic segmentation can distinguish the left hand and the right hand, even when they're both out on the left-hand side of the image. So we trained using machine learning, a system which could segment the 3D image. And of course, once it's segmented, it's pretty easy then to just compute centroids of the segmented regions. And now we have beautiful joint positions from which we get Kinect body tracking. How did we generate training data for the semantic segmentation? We couldn't even get humans to label these images because, of course, humans would disagree. They'd be fine about what's a left hand and what's a left hand and what's a right hand, but they would totally disagree about where the middle of the body is or what, how much knee there is. So obviously, we're going to use computer graphics, which again then wasn't really possible to use computer graphics as training data, but because it was a depth camera, it allowed us to use computer graphic training data. And then, of course, the big innovation that we made in those days, which was another reason that we knew the Xbox people were serious, was so they came to us and they showed us this, dancing thing, and I said, "Oh, all right, fine, yes, brilliant, that's really good, you can do it." We still don't know how to make it work, reliably frame after frame. Then Jamie had that idea, and then we went back to them and said, "Okay, fine, we think we can make it, but you're going to need to take your camera around the world to 10 different houses and video people in their living rooms long before we tell you we can do it, right? Long before we solve this problem, you're going to have to video people in their living rooms." We knew they were horrifyingly serious when they phoned us from some living room in somewhere in Germany or Japan, asking, something like, "Do you want the camera portrait or landscape? Do you want it, at the back of the room or top of the TV or the bottom?" The second time we asked them for lots of money was we said, "Okay, we've got this idea for training data, but basically you're going to have to get a Hollywood studio to render us 1 million frames of training data because they've got the computer graphics experts. We can't do it in-house. It's going to cost you like $1 million." So of course, Xbox people said, "Okay, fine, we're going to spend $1 million. How do you want to do it?" And I love this video we made around the time. So they designed a huge range of people of different shapes and sizes. They went to a motion capture studio to get realistic poses of people playing these games. This is just one view of the training data, where if we put all the heavier people in one space and the lighter people in another, then we can spell out Kinect. But I think it was the first time when we really thought, okay, 1 million training images is a good number. We know we can make progress then. Something else I want to mention just around here. For Kinect V1, we were incredibly careful to test the system on a large range of skin colors. So sometimes today we talk about bias in AI, and we sometimes want mathematical techniques to remove bias, but actually the most important tool in removing bias from an AI system is in here. Right, in your brain. The most important tool is to think about how bias might occur in the system. And the most important tool is to test it on a range of skin colors. So we were specifically, for example, looking for very dark skin, very shiny skin, also very matte skin. We were just trying to think of different ways in which human skin could confuse the camera. And that was super helpful in Kinect V1. And Kinect V1 did not have, did not have any racial bias difficulties. We did have skin color bias in V2 when we introduced face recognition. And of course, nowadays, face recognition is one of the main areas where we focus on bias. The reason we had some difficulties with face recognition in V2 was just we thought we had solved the problem in V1. We didn't go back and check we'd solved it again in V2, and that was just something. So Kinect was good. Kinect sold very well. It was fastest selling consumer device on record. But as you probably know today, it's not played very much. Although again, lockdown story, we are really enjoying playing Kinect at home. It's another good way to get exercise. So if you've got an Xbox 360 and a Kinect, I recommend you dust it off and play Kinect Sports or Kinect Adventures. It's a lot of fun. And this story is relevant again today because just now, or just recently, we've noticed that. I always think it's funny. If you think about Kinect V1, it was released. Xbox peripherals have incredibly careful encryption on them, so that you can't make a fake controller, which gives you an unfair advantage in a game. It turned out that essentially took the decision not to encrypt the connect depth channel. So in principle, you could cheat a connect game by sending rendered depth images down the line and fooling the Xbox. But people don't want to cheat at a connect game because the reason you do it is for fun, for exercise, for sport. But of course, the decision not to encrypt the camera meant that, as we know, suddenly connects were everywhere in computer vision and robotics. And when it looked like the product was discontinued, Connects were selling for higher and higher prices on eBay. So I'm really pleased now that we've released this new Azure Connect development kit, which is a beautiful new camera, much better than the Connect V2 camera, really compact and just useful for lots and lots of stuff. So I'm hoping you're all those of you building real world systems or real world systems that need to work are enjoying this camera. And again, just to sort of reiterate the key story of making this product work, you don't always get the innovations where you think you're going to get them. So I was the person working on body tracking, and yet my algorithms played no part. The only part I played was obtaining training data or working on training data. Jamie was working on semantic segmentation of farm animals, not because Microsoft was going to get into the farm business, just because it was a hard problem, right? Semantic segmentation was a hard problem in 2006. It still is. And that work was what turned out to be key. So you always have this blue skies research, which suddenly turns into practice. The key then that where Jamie was phenomenal was actually following it up and making it really work in the real world with just lots and lots of testing and lots of training data. Is that a question there? Okay, sound is there. Good. All right, final part of this is how did we end up working on hand tracking for HoloLens 2? So I just realized this today as I was looking at this deck. I'd been working on human body tracking, and it turned out not to be useful for Connect. It was useful for other reasons, right? It taught me about machine learning and, taught me about integrating model fitting and machine learning. Jamie was working on animals, so maybe I decided to work on animals. Actually, I didn't. What I wanted to do was work on something that was harder than tracking a well-known object class like humans. Right, so my idea was, humans. It's worth building depth cameras for humans. It's worth building special 3D models for humans because it's such an important object category. But wouldn't it be nice if we could just get 3D models for anything that you wanted to look at? So, for example, I just picked dolphins because they looked like not too hard, but harder than simple stuff. Why dolphins? So what do I want to do? What's the problem we want to solve here? And it's kind of a fake problem, but it's a blue skies problem. The problem is, give me some number of images of some 3D object category, right? In this case, it's dolphins, but the system doesn't know that. The system just knows there's something in common between these images that has generated these images. How can I learn or adapt a 3D model so that it explains this object category, right? So maybe I can show what I mean by showing the answer. So the answer is, what I want to do is, start with a sort of simple template of a dolphin, and then have the system automatically determine a range of modes of variation or basis shapes for the variety of dolphins. And the system should automatically give me the sliders and the slider positions for each of my training images. And we're going to do this by fitting a 3D model to the silhouettes of the dolphins. Why the silhouettes? Because all of our previous work on structure motion had depended on high contrast points. And I was bored of high contrast points. I wanted to use the silhouettes. And our idea was that maybe if you could do this, then maybe you could take a new image, like an image of the same class, but a new member of that class, and then determine the slider positions for that image, which would let you pop out a 3D drawing, right? My idea was, I don't know, maybe it would be a PowerPoint thing or a Paint 3D feature that we could have in Microsoft, and people would, pop out a 3D drawing. What were the tools we had at our disposal? Well, we had point tracking, but we didn't like point tracking because there are no points common between dolphins. Actually, that's not true. There are like 6, right? There's a few points that you can identify, tips of like the nose, tips of fins, and so on. So a very small number of 3D points. And then there's this big clue to the object shape, its silhouette, which is notoriously hard to deal with mathematically. But again, that's what we wanted to do, pop out the shape from the silhouette. So how do you do it, and how do you solve any problem like this? Well, it's probably a good idea to read some literature. So we read the books by Kundering and by Roberto Cipolla and other people, which told us the mathematical concepts, right? The silhouette of an object is this curve out here. The silhouette is the 2D curve. I'm going to call it SI. And the 2D curve is made by a corresponding 3D curve, which lives out on the object. And what's really annoying is that if you change the camera position, if you change your viewpoint of this object, the 3D curve, the contour generator is going to move around the object. So it's kind of not a fixed 3D curve. What are we going to do to represent 3D objects? Well, we're going to use a triangle mesh, just like we do in computer games. So the object is going to be this surface M, and this surface M is going to be a mapping from a set of triangles to 3D. So what's a triangle? It's a 2D thing, and we're going to map from triangles to 3D. And down in those triangles, I'm going to have this thing called the contour pre-image. It's like a little line drawn on the surface telling me what gave rise to the silhouette. So my point in this slide is just, when there's some mathematics there, you may as well understand it, even if you're going to hit the whole thing with, some deep learning regression or something later. You may, even on the weekend, you might want to read about the mathematics. So, we crunched some numbers, and we could build sort of okay models of things like, pigeons. It worked okay on dolphins. It worked okay on pigeons. We did some nonlinear optimization. It was all pretty good. It worked terribly badly on polar bears. Why? Because pigeons and dolphins, you can't see their joints. Whereas on polar bears, on polar bears, they have articulated components to them, right? So, and we were trying to model articulation, something with a skeleton, just with a few sliders and a linear combination of basis shapes. It worked okay on bananas. This was relevant because even then the state of the art of shape from silhouette from bananas wasn't very good. So this was a good advance. But how is it going to be useful in the real world? Well, we immediately thought this skeleton problem is a real problem. So we converted our dolphin tracker into a 3D hand tracker. What had dolphins taught us? Dolphins had taught us how to deal with 3D surfaces using a tool called subdivision surfaces. It had taught us how to very efficiently fit models to sparse data. Now, the sparse data in dolphins was silhouettes, which is hard. In the video I'm going to show you, we're using Connect data, so fitting hands to 3D data sounds easier. But it was a valuable improvement.
Physical manipulation of.
And what we were able to do is use a Connect to fit the human hand. So there's the Connect down here looking at the human hand. And we had this dream that user interfaces would be so easy to use that you would just use real world physics. And of course, we were worried about whether it would matter that you don't feel anything. There's no haptic feedback. It turns out that this, if I go back to this, just this one section, it turns out I thought it was going to be really important to make this slider really thin, so that when you grip the slider, your fingers would touch each other and you'd get a sensation of haptics. Turned out that was completely wrong. The best sensation is the one you get just at this point, not from the two-handed interaction, but when you tip the thing and it moves. And if you get to try a HoloLens 2, I think it's worth, really try just single finger tapping things. You get this amazing feeling as if there's a real world haptic feedback in there. So we turned dolphins didn't turn into any product, but gave us the tools to understand 3D surfaces, which we were able to use. Now, this is on a Connect V2. The algorithm that we used for it, I'll skip over that, ran on sort of 750 watts of GPU, if I remember. Now it's running, as I say, on 100th of an iPhone 7 in the HoloLens 2. And this is just showing some of the interactions that it enables. So you can pick up an object and spin it around in 3D. So how do we make accurate hand tracking on this tiny device? Well, it's the same old story, right? We're going to have to collect an awful lot of ground truth. Even if we weren't using machine learning, we would need to get ground truth for testing. But of course, our system is going to be a hybrid. The first system I showed you was pure model fitting, Buju. The second system Connect was essentially pure learning. It was random forest, not deep learning, but it was basically pure deep learning with a tiny polish up at the end. What we found is that if your model is pure geometry or pure deep learning, you do much more work trying to make it good at the things that the other one is good at. So this model for HoloLens is going to be a hybrid. We're going to use deep learning at the front end, again on a tiny device, super efficient deep learning, and then we're going to use model fitting at the back end. And that combination is going to give us our 100th of an iPhone compute. So what are we going to do to make hand tracking operate? We're going to collect some ground truth. We're going to learn about a model. We're going to use machine learning. What ground truth did we collect? We built ourselves a multi-camera rig. We got ourselves 150,000 hand poses. And again, the system hasn't been built yet. So we're asking the users, just kind of pretend you're playing with some future HoloLens. Do hand gestures that you think will be involved. And we kind of give them some idea. Maybe they're sliders. Maybe you're playing around with stuff. So we had people just play around in this custom rig that we built. You might think, oh, it's lucky at Microsoft you have lots of money. And yes, that's absolutely true. We can put money behind something like this in order to make it work. But also, rigs like this exist in academia. So Michael Black's lab in academia, built a fantastic human capture rig. It is possible. And it gives you such an advantage in later stages. So one of the things about this rig is that we're using tens of cameras here. We're not limiting ourselves to the small Kinect that's going to be on the HoloLens headset. We got 100 different people. And of course, we remember to make sure we have a variety of skin color reflectivities and other characteristics. And also, we used we had manual markup. So one of the big innovations, I can't remember if it's on the next slide. No, it's not here. So if you look in this video, and maybe it's hard to see, but what we're showing here in gray is a model fitted using maximum compute, maximum everything. This is our most accurate model, fitted with manual assistance to every frame. So we have ground truth for what model fitting should look like on this sequence. If you look into this sequence, you can see the green dots. That's the kind of the raw data to which we fit the model. So we made some key innovations here, just in how you label the data. So how do we first label the data? Well, what we first did with the data was we thought we were very clever. We had a sort of an online model fitting. So you take the gray thing, you'd position it on the image, and then you try and use the mouse to drag the gray finger, thumb tip to near where the green data corresponding to the thumb is. Turned out doing that in 3D is kind of a pain, right? You kind of drag, and then you got a different gesture like shift click to rotate, and then you drag again, then you rotate. What was much better was for us to just click roughly in the area and say thumb, index, middle, ring, pinky. So you would click, on the fingertips. But even that, we had bad user interface design, because what we had was a menu where we would say, right click here, select, is it the thumb, is it the middle finger? What was much more accurate, and this was, a good invention, was you place the mouse over the thing you want to indicate, and you use the keyboard, QWERT, to indicate whether it's little, which finger it is. So your hands never move from the keyboard on the left, your hands never move from the mouse on the right, and you never click the mouse, because when you click the mouse moves a little bit, and you miss your thing you wanted to click on. So we probably got 10x speed up in human labeling time by just really careful design of the user interface of the labeling tool, which was something we were just going to throw away after 3 weeks. But spending effort on that, saved us lots. We also needed to do synthetic training data. Synthetic training data for a time of flight camera is much more difficult to simulate. It's much more difficult to simulate than it would be for a structured light camera like the Kinect V1. So we made a fully, as realistic as possible, visible light RGB system. You'll notice that the motions here are the same as the motions from our rig. So we use our hand models from the rig to inform the CG models, which we can now play in front of backgrounds with difficult scenes like bright light coming in. We can simulate the depth camera. And of course, we can simulate machine learning ground truth. We can simulate lots of data capture to get the 3D models, and then the 3D models go back into the synthetic system to generate machine learning ground truth. And again, you will have seen there the little semantic segmentation labeling that, again, we're using same sort of technology as was used in Connect. Finally, I said we needed to make it fast, and boy, do we need to make it fast, right? So when we that we were making it fast on, we have 2 cores, each running at 500 megahertz, not gigahertz or anything like that, and each core has 128 kilobytes of RAM. And we needed to optimize the code on this. I won't go into masses of detail, but basically say we didn't write the assembly language, but we wrote the C++ and then observed the assembly language cycle by cycle. We went to floptable. Sometimes people will tell you that if your machine is, I think this is 4 megaflops, I think, this machine. People will tell you, oh, that's what the manufacturer bills it at, but it's impossible to achieve that throughput. No, you can achieve that throughput. You just need to write your code very, very carefully and be very careful about how the assembly language is generated. There is no PyTorch TensorFlow in here because, you know, we can't have a runtime interpreter. Because our matrices are not huge, right? We've only got 4 megaflops to play with. Malloc is done on the whiteboard, so if you want memory, you go into the next office and you ask somebody for some memory and they have to lose something from there. We tried simplifying our models, and yeah, we've had some nice results on that, where if we go back down to polygon model from subdivision surface, it's a disaster. So here we are. Over a couple of years, we sped up our code by a factor of about 250, and that was already, you know, the world's fastest code. And as we do that, we move, you know, it's really important that as you make your code faster, so down here, down is faster, you're sometimes going to make it less accurate. So you have to then make it faster, get the accuracy back. That was a lot of fun. All of which leads us to this video
Now, not only
of
does
Julia showing us the first public launch. This was in February, of the hand tracker. This was an early release, very glitchy. But look, this is the 3D hand model that she's viewing in this battery-powered device, powered by our algorithms. So we were super excited and proud of that. So to conclude, you know, I've talked about commercializing various types of computer vision algorithm, moving from, you know, classic geometry in the 90s up to hybrid geometry deep learning today. I'm going to hypothesize that a lot of algorithms that need to run in low compute, and remember, low compute isn't just on the HoloLens, right? If you're Microsoft or Google and you're selling you know, sort of an email autocorrect or auto prediction or an email sorting system, every time you run, you know, a trillion parameter model on a user's email, you're spending real dollars. So I'm sort of obsessed with efficient modeling and machine learning, but for me, big data goes with efficiency. And I'm now delighted to be leading this team of people working on, as I say, all data AI, on big data, small data, and things that are messy, things that go beyond the regular tensors of computer vision and machine learning. Thank you.
Yes, Andrew, many thanks for this beautiful presentation. I really love this historic flashback from all the old products to the really novel things, and it's really exciting to be we are living this kind of age, and we are really able to live and observe this kind of development our kids are taking for sure. So we have time for a couple of questions. You can send the questions in the chat if you like, or we can also just raise your hand somehow and give a note if you want to raise a question. Maybe I start with a question. I really like the approach of making the transition from research to practice. And I'm wondering, how do you deal with hyperparameter optimization in a product?
Ah, exactly. Okay, good question. So this is back to my point that when you're making a product, the test data is completely unseen, right? The test data is actually what happens to the first 10 journalists who try it, right? In some sense, you're going to make this thing, you're going to ship it. It's probably going to be launched at some press event or some big event. As the first 10 people who try it, if it happens not to work on them, then it's pretty hard to recover, right? It's pretty disastrous. So there's a test data. The test data is not, the sort of evaluation on a huge held out, huge set that we might think of. It's almost like you need to minimize worst case. So the worst case is that it happens that the first 10 people who come are incredibly tall, right? And, their hands are big and it doesn't work on them. So what does that mean when you're back over in training land, right? Before you release the product? What it means is this: it means that every parameter is a hyperparameter, or hyperparameters are just parameters. The way you have to set them is by careful, you could call it cross-validation, but you really hold on to a test set that you believe in, that is as hard, you make a test set that's as hard as you can make it, and you never optimize on that test set. Like, you might test once a week, or you might test only when all other metrics give you a hint that it's a good idea to test now. That's the kind of time you might test. So hyperparameters and parameters, they're all the same. You might have to grid search your hyperparameters. You might have to do whatever it takes. You may well do finite different gradients to optimize, but there's always a sort of careful test set that is the thing that's super held out. I think that's an answer to your question, or maybe it's an answer to two questions related.
Yes, exactly. And I completely agree. And then you have all the other problems about imbalancedness in data, about domain transfer, and so on. And it's really hard to be able to deal with this. And everyone has to think about what could be cases happening when people try it out and play around with it. Okay, here I see a question in the chat. Maybe Yang, you can just switch on your microphone and raise the question.
Sure. First of all, Andrew, thank you so much for sharing the mistakes and success with us. It's a very much a fun journey, and we really appreciate that. So I guess all of us learn from some failures someday, one or the other. So the question is, could you tell us what's the most important lesson that you learned from the previous failures?
Wow. Yeah, so many to choose from. Failures, I mean, and lessons. Oh boy. So this is going to sound a bit silly, but always assume you might be wrong. Really, like, and at the same time, it goes with have conviction. So, I've stuck with this kind of model fitting paradigm for a long time, right? But my assumption, if I were building the hand tracker for HoloLens, my hope was that every day that we'd be able to use deep learning end to end, right? And that would basically kill my entire career. I don't care. I don't mind. I just want to, I'm in Wikipedia now. I tell you, I put that there myself. I really wanted deep learning to take over, because remember, if it did, we would have saved like half the flops. In fact, if deep learning started to work, we would have thrown away all the flops that we had devoted to model fitting, and then we'd have had twice the many flops for the deep learning model. So I was really rooting for the rival technology, but of course, at the same time, I was giving every piece of commitment I had to the design of the model fitting technology. And I keep saying I here. I'm just like one person on a team, but it's just that I'm kind of the person associated with this model fitting technology. So massive commitment to the one you do believe in, but really try and make the other one work. After a while, I began to realize that the reason a hybrid is good is model fitting is disastrous. If here's the ground truth, and I start my model exactly one finger over, it's never going to recover, right? There's a local optimum there that the model is, is never going to notice that this finger over here needs to, so the model fitting is disastrous for getting out of, it could start only 2 centimeters away and not get into the right minimum. But at the same point, deep learning is great for getting you within a centimeter, right? Getting roughly the fingertip. but it's not going to get you the last millimeter. There's kind of, you need too much model capacity to get the last millimeter. Okay, so now I'm telling you how we didn't make a mistake, but the mistake that I think I've made earlier is to hope that the other guys are wrong. I think you've basically got to got to work just as hard on the other guy's stuff as on your stuff, and really, accept that you're probably wrong.
Yes, thanks for this
Thank you.
nice answer. I also think for younger PhD students, it's always important to teach that you have to keep your whole lifetime an open mind, and you must yourself allow to make mistakes. And even if your neighbor is dealing with how to segment a cow, this is always an important piece of work. You can later make use of it. So never speak bad about the research of other people. And I think once you have this open mind, then also research will be much easier and also much more joyful.
Yeah, and if I could just comment back on that as well, I don't know if it's still true among young academics, but when I was a young academic, we were always told, oh, you have to get a thing, you have to have, pick a thing and be famous for it, and there was always this idea that you would have a feud, right? That there would be so I wrote a paper 20 years ago on the iterated closest point algorithm, and I said, I don't like the ICP algorithm. Here's an algorithm that I think works better. Be absolutely sure that when I needed to do model fitting for HoloLens, we went right back to the ICP algorithm to check if that was the thing we needed to do, in order to go fast. And we also implemented, I think our implementation was probably hundreds of times faster than the state-of-the-art ICP algorithm, because we needed to check. And in fact, the one that we've got is a little bit of a hybrid. We do actually do an ICP step after every model fitting step, but we turned off the model fitting step. Of course we did, right? We could have saved 100 megaflops, and things got worse. So again, you need to be open-minded. People think, oh, Fitzgibbon, he's got a feud against ICP. Absolutely not. It's just that most of the time it doesn't work for me. So like, not only do I think you shouldn't try and, pick one thing, but I think you definitely shouldn't be against other things. Same as you were saying, but yeah.
I also still teach ICP in my lectures. So, okay, so here's a final question from Saksham Zuri, and I think that we have to continue with the other talks. So, Saksham, do you want to raise your question?
Oh yeah, so I just wanted to ask, first of all, thank you for the amazing talk. The examples were really good. And my question is that is it more sensible to maintain a evolving test set, like in your case, so that you have a sequestered property so that you never overfit? Because even if you test on it one every week, you'll kind of end up overfitting to it at some point.
Oh yeah. I would say there's two things. Number one, like in the first example, I was talking about Bougie, where we had this test set of 100 videos. A lot of the overfitting we could design away without changing the test set, just because the overfitting was like some stupid metric, right? We could improve the metric, and suddenly we weren't overfitting anymore. But to be honest, I would say, our example, 100 videos, then throw them away and get a new 100 videos is just one instance of evolving test set, right? It's like, we did throw away the first 100, but of course we checked like that we hadn't lost, so really it's wrong to say we threw them away, but as we now had a 200 set. So yes, evolving. And sorry, I've made an assumption. I've assumed that by sequestered you mean kind of separate test and train.
More like unseen kind of stuff, like say you have different cameras, maybe you see something new basically, which is different modality. I
mean, Bodo mentioned domain adaptation, and your test set is of course the one closest to reality. So you might be training on synthetic data and testing on, training on synthetic data, validating on synthetic data, but you then test on real data. So there's super sequestration of one golden test set. And basically, it's a bit like I was saying about bias. You just kind of have to use your brain. You have to think to yourself, am I overfitting? And be critical.
Yeah, there should probably be a mental aspect to fighting bias than just putting stuff in the model to fight it.
Yeah, exactly. Put it in, of course. Put stuff in, but really think, why would that work? Why would that? And then, of course, poke it as hard as you can with hard examples.
That's right. Thank you.
Welcome.
All right, Andrew, many thanks for this beautiful presentations. I think for the second round, people might ask you questions via email. And
Sure.
we can't clap, or will you be available? Or
We'll see. I'll see if I can get up for 7:20, but you know, I might not. It'll be Saturday morning, but I'll see if I can do it.
yeah, exactly. So, but many thanks for having you here. And
yes, so maybe Paolo, can you then continue?
Hi, my name is Elad Amrani, and I'll be presenting self-supervised object detection and retrieval using unlabeled videos. This work is an IBM Technion collaboration and was co-authored with Rami Ben-Ari, Nibar Shapira, Tal Hakim, and Alex Bronstein.